Here we go, here we go, here we go. All right, video number 2 of possibly 3 videos. The last videos of this Unit 16, or the last lessons, not videos, the last lessons of this Unit 16. Here we go. Today, we're talking about infinite series. So let's get to it. It says find the sum. Now, wait a second. It doesn't say find the sum of the first 10 terms or 15 terms. It just says find the sum. And then I notice it says dot, dot, dot. So this just means find the sum forever. So I'm noticing the terms are doubling each time. So I made a little graph. The first term is 2. The next term is 4. The next term is 8. The next term is 16. I know that's not where 16 is. 16 is more like here. Sorry, everybody. All right, but if I were to graph this thing, where is this graph going? As I go further and further to the right, where's the graph going? Is it going, in other words, is it converging to a specific number? Or is it just going on, as the fine spaceman once said, to infinity and beyond? That's where it's going, okay? So in other words, let's go back to limits, which is what you covered at the beginning of the year. The limit as n goes to infinity of this particular sequence is infinity. There is no particular sum. Now, it could, because sum has to be a particular number. And how we say that in mathematics, this system diverges, or this series, not system, this series diverges, right? Because it goes to infinity, and infinity is not a definite number. Okay, so any series that goes to infinity as you go further and further up the whole number chain diverges. How about a series like this? 1/2, then a quarter, and then an eighth, and then a 16th. I drew that on a picture as well. So after one term, you're at a half already. And then after the next term, you add half of that, which is a quarter. So now you're at 3/4. All right, and then after for the next term, you add half of that. So add another eighth. Boom, now you're at 7/8. And then you're at, what is it, 15/16. You're getting really, really close to this dotted ceiling. Notice how I did a dotted line right there? That's an asymptote. And that's exactly right. That is an asymptote. Over here, you're at 15/16, and so on and so forth. Oh my gosh, you're getting so close to 1. Are you ever going to touch 1? By the way, this is 1 right here. Will you ever reach 1? You want to reach out and touch it, but you can't. All right, it's an asymptote. But this asymptote right here, and I'll draw it in a different color as well, this asymptote is the definition of an infinite sum if it exists. An infinite sum is an asymptote. It's a value that you approach but never quite get to. But notice how all these terms are getting closer to or converging to the number 1. That's the infinite sum right there. Okay. And by the way, we're going to learn in just a minute how to find that infinite sum value. Like Mr. Clody, we're just going to have to know, what this infinite sum is going to be, where the dotted asymptote line is going to be. No, you don't. We'll find it. All right, 1, 3, 5, 7. Now, first off, this is arithmetic, and we're adding by 2 each time. And the terms are getting bigger, larger, and larger, and larger each time. You add 3, then you add 5, then you add 7. It's going to not look exactly like this, but yes, it's going to just go up to infinity. So it's going to diverge. Okay. How about this one right here? 1, then -1, then -3, then -5. Time out. We're subtracting 2 each time, aren't we? And so it's arithmetic, and the common difference is -2. And so if you add them up as you go, you're just getting further and further negative. So you're approaching not positive, but you're approaching negative infinity. So the bottom line is a system diverges whether it approaches positive or negative infinity, but it only converges when it converges upon or when it approaches a specific value as you go out to infinity to the right. So let's think about this. What was unique about this second example? What was unique was that the subsequent terms got smaller and smaller and smaller. And what also was very, not unique, but just something about it, a pattern, it was geometric. And the R value needs to be one in which when you multiply by it, your terms get smaller. What kind of number can you multiply by and have your subsequent terms get smaller and smaller? Any number that is between +1 and negative 1. Okay, so I'm just going to say this. If your R value is between negative and positive 1, the series converges and an infinite sum exists. And once you establish that R is between positive 1 and negative 1, and by the way, that's exactly what Mrs. Middleton wrote right here. The absolute value of R has to be less than 1. It's exactly correct, and this is just another way to write it. And your formula, I'll put it in a wavy circle, is right here. As long as your R value is between positive and negative 1, an infinite sum exists, and that's the formula. The first term divided by 1 minus R. Piece of cake, yo. All right, so let's do it. Find the sum in example 5. Let me not scroll down too much. Of this particular series right here. First, let's find R. R equals the second term divided by the first term. Remember, dividing by a number, that's equals. Dividing by a number is like multiplying by its reciprocal, so 4/3 times 1/2 is what? 4/6, which reduces to 2/3. And that's what's right there. Is 2/3 between positive and negative 1? It is. Ding, 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 ding. So to find the infinite sum, Glade commercial, plug it in, plug it in. Take the first term, which is 2, divided by 1 minus R, 1 minus 2/3. 1 minus 2/3 is 1/3, and then 2 times 3, because 2 divided by 1/3 is 2 times 3, is 6. There you go, boom. So what does this 6 represent? This 6 represents that ceiling right there. That is where the asymptote is that your series will approach, the infinite sum. That's it. Congratulations, you found an infinite sum. Let's do example 6. Find the sum to infinity. All right, and so right off the bat, I know that R equals 2/5, because whenever you're raising something to a variable exponent, you know it's geometric. 2/5 is between positive 1 and negative 1, so just plug and chug. So 3 first term divided by 1 minus 2/5, so that's 3 divided by 3/5, which is the same as 3 times 5/3. The 3's cancel, and you're left with 5. This may be one of the more simple formulas to use, is it not? My goodness. Once you understand that R is between positive and negative 1, you are golden. All right, here we go. Example 7. If geometric series do converge, there are intervals of convergence. What does that mean? It's basically stating that R has to be between 1 and negative 1. These are the intervals of convergence. If R is greater than 1, it diverges. If R is less than negative 1, it diverges. So find the intervals of convergence for this particular value right here. All right, so what is R? Take the second term, divide it by the first term, and you get R. So R is negative 2x. So that's where this comes from right here. All right, so I know that R has to be between 1 and negative 1. So just take a look at what Mrs. Middleton did right here. So if R has to be between negative 1 and 1, then negative 2x specifically has to be between negative 1 and 1. Then if you divide everything by negative 2 right here, you get positive 1/2. Now remember, algebra 1. What happens when you divide or multiply by a negative number? Your inequality sign flips. And so this less than sign, let me use the cursor, this less than sign becomes a greater. This less than sign becomes a greater. And if you want me to rewrite it so that it's going in less than form, here it is. And so you could also write it as soft brackets, negative 1/2 to positive 1/2. Those are the intervals of convergence. Otherwise, the series will diverge. I keep wanting to say system. Series will diverge. Find the intervals of convergence for this one. All right, so what's R? R is x plus 2 divided by 1. So R is just x plus 2. So x plus 2 has to be between negative 1 and positive 1. This really isn't so bad, right? Subtract 2 from both sides, and your intervals of convergence are from negative 3 to negative 1. Booyaka. There you go. Okay, so now we're going to find an infinite geometric series that converges to the number 4. Ooh, so we know it's an infinite series. So that means we could use this formula right here. The first term divided by 1 minus r. All right, and I know that the infinite series converges to 4, so it equals 4. First and foremost, you have two variables here. Can't deal with two variables at once, so let's get rid of one of the variables by making it a constant. Why don't we just select our first term to be 1? Mr. Cody, you're allowed to do that? Sure, why not? By the way, Mr. Cody, could I have made my first term be 10? Sure. It's your world, I'm just living in it. Okay, so since we chose it to be 1, 1 divided by 1 minus r equals 4, then you're just solving the algebra 1 equation, and r equals 3/4. Remember, it says find the infinite geometric series, so you can write your answer in one of two ways. Yes, r does equal 3/4, but that's not the answer. We know that the first term is 1, so then 1 times 3/4 is 3/4. 3/4 times 3/4 is 9/16, and so on and so forth. Don't forget to do plus ... So this is one way to write your answer. Or if you wish to write it in sigma notation, you could say the sum as any variable, in this case, Ms. Middleton used k, as k goes from 1 to infinity, of 1, the first term, times r, which is 3/4, to the k minus 1 power. Again, that's your choice, whichever way you choose to write that series. Last example, and I'm done with you. Something that you did back in middle school, believe it or not, writing an infinite decimal, a repeating decimal, I should say, as a rational number. We're going to write it in fraction form. So if you really think about it, 0.13 repeating is the 0.1, that's on its own, but then plus 0.03, and then plus 0.003, and 0.003 infinitely. So so it's basically 0.1, this is on its own island, plus this infinite series right here, and r is going to be 0.003 divided by 0.03, which means r equals 0.1. And that's what's right here. And the first term of this geometric series is the 0.03. Okay, so you're going to take this infinite series, the first term 0.03 divided by 1 minus r, and then plus the 0.01. Let me, that's the 0.01 right here. Okay, just want to make sure you understand which is which. So that's 0.03 divided by 0.9. 0.1 is 1/10, is it not? Yes, yes, yes. Okay, and so how did Mrs. Middleton get this right here? What did she just do? Okay, well, if you really think about it, if you move the decimal places over here, this is what, 1, 2, so that's 3. And then if I move this over, that's 90. Okay, and so all she did was she worked this through. And so then, I'll be honest with you, this 3/90, I would just move the decimals over. See 3/90 right here? Exactly what she wrote right there. If you want to skip over this middle step, completely your call. Like, you don't need to write all this if you really don't want to. You could just say 3/90 plus 1/10, then get a common denominator, 3/90 plus 9/90, that equals 12/90, which reduces to 2/15. That's it. Okay. By the way, what Mrs. Middleton wrote here is completely correct. I thought I might save you a step. Just move your decimals over, middle school style, two places, you got 3/90. 0.1 becomes 1/10, then common denominator, and reduce your fractions. Questions? Ask. Lesson done. Bye.